Hello everyone, this is Alex from the Onchip team from Universidad Industrial de Santander at Colombia. So this is going to be a quick presentation, about 5 minutes, of the work we made in the Chipathon 2025. So this is the picture of the top chips. So we can see here we are number 6. The number 6 here, we made a current reference generator. We're going to go into it. This is the schedule we will follow for this presentation, and let's start with a quick overview. Just as a reminder, all this work has been documented in the GitHub repository, so you can access to it. This is the circuit we built. There is a current reference generator that is pretty standard. So we take voltage, very constant voltage, usually from a band gap or a very stable source. And we use a reference branch to mirror a current, and so we can provide different output currents. So the idea is to build this in a programmable way, so we can have different outputs with different values, can be p-type or n-type current sources, and we're going to test that. This is the project tracker, so we can see three main stages that are the work related to the error amplifier, then integrating that error amplifier in the current reference generators with the mirrors and the compensation, and finally integrating all that circuit to the chip level and routing to paths and running LBS. We have a specific detail here in the LBS, so we didn't achieve to verify completely the chip, and we are making progress about that with all the track and the team members. And then this is the proposed flow. So we have the specification, and this is what we did, and the designer makes the designer work, the design, and we have here an automated framework that takes the device sizing and matching matrices, so we can match some devices. From that, this is case verification, and we can directly run this loop for improvement in the design. About the schematic, this is the schematic implemented in a scheme. We have the folded cascode, so we have at the left bias circuit and the right core circuit. This is the table, the specification table. So the idea was to have high gain and low offset. So here we can see up to 80 dB in the gain and up to 10 millivolts, 3 sigma of the offset. These are post layout results of the design. So we have these values, and the objective is achieved. So we connected this amplifier to the output stage and using this node as undirected compensation. Finally, the output currents are made from a reference of 2 microamps. The feedback forces this node to 1.2 volts. We place a resistor there that actually is an external resistor, expected to be 600 kilo ohms from there. So it is kind of good to have this outside the chip. So this guy is the main error source of the circuit. For the case validation, we have developed all the case flow and documented it in the GitHub repository. That we translated the schematics from the scheme to use the case variables, so we can have parameters here from case, from the YAML file that is written this way. So we can have different values for the VDDs and process corners, and that makes more efficient the validation across corner. So we have different schematics for different specifications we want to measure, and these are the final results, where we can see here in Monte Carlo, the Monte Carlo simulation achieved the expected values. And from that, the automated layout was or consists in this flow. So it is based on Glayout. So we have the Glayout framework that is in the GitHub repository, and we from that we start working to build some function, some auxiliary function, what we call support functions, to build matching techniques, matching arrays, and to facilitate the connections. Here we can see an example of the output, made by this framework. So it is the core amplifier of the folded cascode, and finally we placed power rails to supply them. This is an example of how it works the matching technique. So we can have input matrix to have that physical distribution in the layout. This is an example of a current mirror, a p-type current mirror to implement the to explain the power rails function, so we can have directly connected to the power rail. This is the final layout, so where we can identify each one of the parts of the layout. And an important point here is that the amount of outputs and the value of that outputs are preset, and then they are specified by these two lists that shows in this case, for example, they are 1, 10, and 25 times the reference current, that is 2 microamps. And here is where we can see the different outputs. For up we have the p-type, down we have the n-types, and here it is a compensation, the capacitor for the compensation. And that's the layout. And finally, some conclusions that what we did, that it was completely out of experience, and what we feel that worked fine was to we did it. We achieved the tip out, and we learned really a lot of things about the tools, and from Scheme, CACE, Glayout, Glayout, and even from GitHub. And it was really a lot of work and a lot of learnings. And finally, the templates. The container it is really powerful idea that we can have everything standardized. From the pending side, we have the facts that well, we actually didn't use magic, but many people use magic, and some of the committee members actually prefers magic. We don't know about that, and why it is better magic than Glayout, or vice versa. And we also made LBS only for most transistors, and we had some complications with, for example, min caps or resistors. And finally, the documentation expected for the flow we must follow were not that clear. So and we believe that are the points. Finally, for the feedback, we feel that there was really an effort we have noticed to maintain constant communication, working with all the teams. And in the future, we will like to see the possibility to taking out in Sky 130. There is kind of interest, and we understand what this final point is kind of a lot of work, but maybe we may need tutorials on how to properly develop what we mentioned about the flow. So what are the expected steps we should follow to develop a design, and about the tools also. We take some time to learn how to properly use each tool. And that's it. One more time, thank you, Sadiq, for all the work made, and all the committee members. We are Onchip team, and thank you so much for your work.